Hi future scientists, this is Ma'am M and I will be your Science Saya mentor in Science 8 for today. Science 8 Unit 1 Module 3 Grade 8 Force, Motion and Energy. Part 3 Sounds. Sounds. Learning competencies. Investigate the effect of temperature on the speed of sound. Part 3. Objectives. Number 1. Define sounds. Number 2. Determine the effect of temperature on the speed of sound. And number 3. Compute the speed of sound in air at different temperature. Let's review. What is a wave? A wave is any disturbance that transmits energy through matter or empty space. All waves carry energy without transporting matter. It will continue to travel as long as it has energy. What are the two types of waves? A wave can be a transverse wave or longitudinal wave, depending on how they move. Here's an example of a transverse wave. And here's an example of a longitudinal wave. Wave transport energy, not matter. Medium does not move with wave. Wave passes through. What is a transverse wave? These are waves in which the particles of the medium move perpendicular to the direction of the propagation of the wave. Examples are rope and ripples form in the surface of the water. What are the parts of a transverse wave? Here we have crest. It is the highest point of the wave. Trough, the lowest point of the wave. Wavelength, the distance between 2 points of the wave, crest to crest or trough to trough. Amplitude, the distance between the equilibrium and the crest or trough. Equilibrium, the middle point around wave moves. Try this. Parts of a wave. Using the words in our word bank here, kindly label the parts of the wave. Ready? Go! Time's up. Here are the answers. Did you get it right? Very good. Next, longitudinal wave. These are waves in which the particle of the medium move parallel to the direction of the propagation of the wave. Compression and rarefaction are formed. Examples are slinky and sound waves. What are the parts of a longitudinal wave? Longitudinal wave is composed of compression, which is the part of the wave where particles are crowded together, rarefaction, wherein it is the part of the wave where particles are spread apart, and wavelength, the distance between any 2 points of the wave, measured between compression to compression or rarefaction to rarefaction. Let's try this. Parts of a wave. Using the words in our word bank here, label the parts of a wave. Are you ready? Time starts now. Time is up. Let us reveal the answers. Did you get it right? Awesome! Remember, wave is any disturbance that transmits energy through matter or empty space. A wave can be a transverse wave or longitudinal wave depending on how they move. Transverse waves are waves in which particles of the medium are move perpendicular to the direction of the propagation of the wave. And longitudinal waves are waves in which particles move parallel to the direction of the wave. Trivia question of the day. How do we hear? How we hear. Sound waves enter your outer ear and travel through the ear canal to your eardrum. Your eardrum vibrates with the incoming sound and sends the vibration to the three tiny bones in your middle ear. The bones in your middle ear amplify the sound vibrations and send them in your inner ear or cochlea. The sound vibrations activate the tiny hair cells in the inner ear, which in turn release neurochemical messengers, where your auditory nerve carries the electrical signals to the brain, which translates into a sound you can understand. And that's how we hear. Amazing, right? So, to discuss our main lesson for today, let us define sounds. What is a sound? Sound is a kind of longitudinal mechanical wave. It results from back and forth vibration of the particles of the medium through which the sound wave is moving. Next, what mediums can sound travel? Sound requires a medium to transfer energy from one place to another. It can travel through any medium, but it cannot travel through a vacuum. Try this. In which medium does sound travels fastest? In iron steel, water, or air? What do you think is the answer? Yes, in iron steel. You guessed it right. Amazing! Why? Because the denser the medium, the faster the sound will travel. What material does sound travel fastest through? Sound travels through different media differently. It travels fastest in solids and slowest in gases. This is because the molecules in solids are very near to each other, compared to liquids and gases. In the air, one great factor called temperature affects the speed of sound. In relation to temperature, let us try to answer this question. Which location do you think the sound will travel faster, and why? Let us observe and compare the illustrations A and B. A is Puerto Galera, Philippines with air temperature of 40 degrees Celsius. And B, Eiffel Tower, Paris, France with air temperature of 2 degrees Celsius. Take note of the weather and temperature of the two locations. In the air, the speed of sound is affected by its properties, namely humidity and temperature, though humidity's effect is less. It is temperature that greatly determines the speed of sound in air. Sound waves travel faster when the air is heated or exposed in a higher temperature. Molecules at higher temperatures have more energy, more erratic, and vibrate faster. Since it vibrates faster, it can carry sound waves more quickly at higher temperatures as compared to the air molecules with lower temperatures. So, applying the concepts, the answer for the question, in which location do you think the sound will travel faster? The answer will be A, Puerto Galera, Philippines with air temperature of 40 degrees Celsius. The speed of sound at a standard temperature at 0 degrees Celsius is equal to 331 meter per second. It will increase at a rate of 0.6 meter per second for every degree Celsius increase of temperature. Observe the motion of the molecules as we increase and decrease the temperature and pressure. Indeed, temperature has a great effect on the speed of sound. Now, let us try to recheck mathematically if really the answer is A, Puerto Galera, Philippines. So, let's try to compute the speed of sound in air in Puerto Galera using this mathematical equation, where V refers to the speed of sound in meter per second, and 331 meter per second is equal to the speed of sound at standard temperature at 0 degrees Celsius. 0.6 meter per second per degree Celsius refers to the constant rate of increase in the speed of sound for every degree Celsius increase in temperature, and T refers to the temperature in the area. Let's try to answer a sample problem. Here we have two tips, practical tips in answering problem solving. First is you have to analyze the problem. Second, you have to gather all the data or use the GRESA method. In using the GRESA method, you have to first find the given. Start with the given. Then, followed by R, which is required or unknown. Next is E, or equation or formula. Next is S, solution, and then A for the answer. Let us compare the speed of sound in figure A and B. To start this, let us try to compute first the speed of sound in Puerto Galera, Philippines. Applying the GRESA method, let's start with the given, which is temperature 40 degrees Celsius, then followed by the required or the unknown, which is the speed of sound with the unit of meter per second. Now, let us use the equation. V is equal to 331 meter per second plus the product of 0.6 meter per second per degree Celsius and temperature. For the solution, all you have to do is to plug in the values. But take note that you have to do first multiplication, which is 0.6 meter per second per degree Celsius times 40 degrees Celsius, and then the product of that should be added to 331 meter per second. Take note of the cancellation of Celsius units. And A answer, which is 355 meter per second. Now it's your turn. Please calculate the speed of sound in figure B, winter in Paris, France, and describe to which location the sound would travel faster. Don't forget to apply the GRESA method. Are you ready? Time starts now. Time is up. Let us check. Using the GRESA method, you were asked to compute for the speed of sound in winter in Eiffel Tower, Paris, France, with a given air temperature of 2 degrees Celsius. Answer: 332.2 meter per second. So, based from the results, sound will travel faster at A, Puerto Galera, Philippines. Here we have A, Puerto Galera, with the speed of sound of 355 meter per second, and B, Eiffel Tower, with the speed of sound of 332.2 meter per second. Sound waves travel faster when the air is heated or exposed to a higher temperature. Molecules of air at higher temperatures vibrate faster, so it can carry sound waves more quickly. Remember, sound requires a medium to transfer energy from one place to another. Sound comes from vibrations. It is the result when a force, either sound or pressure, makes an object or substance vibrate. Solid, liquids, and gases all transmit sound as energy waves. The speed of sound in air is greatly affected by the change in temperature. Sound travel faster in locations where the air temperature is higher compared to places where the air temperature is lower. Check your understanding. Why is it better to hold a musical event or programs in the evening? Answer: during the night or evening, the temperature of the air is lower, which provides audience better absorption of sound waves. Did you learn something today? I would love to know. If yes, kindly type on the comment section #sounds. Are you ready? Next topic, colors of light. For more videos, don't forget to like, comment, and subscribe.